Hi everyone, I'm Xiaohua Xu from UC San Diego. So we'll be looking at surface deformation nearby the Ridgecrest earthquakes, frictional slip or compliant fault. The left-hand side is the stacked in-surface gradient maps. So there are many places with sharp features in the map. These sharp features are actually indicating strain concentration. Here we call the linear concentrations we saw the surface fractures. The right-hand side is a decomposed east-west component from the full resolution INSAR data. Red colors mean the surface is moving east, and blue colors means moving west. If we look into one of the surface fractures, for example, from the red and blue contrast, it indicates that this fracture is moving right laterally. From the tectonic stress over this region, if these fractures are largely aligned with the main 7.1 rupture, its expected motion should be right lateral. If it is more aligned with the magnitude 6.4 direction, it'll be left lateral. If you do this kind of what we call polarity analysis for all the fractures, you'll see that some of them are moving in the direction of the prevailing tectonic stress, in other words, prograding fractures, and some of them are moving the opposite direction, in other words, retrograde fracturing. So we'll be looking into two of the regions here near the Ridgecrest earthquake sequence. So here are the two regions. So C and E are east-west component, and D and F are vertical and south-north component. If you look into one of them, so these fractures are aligned with the magnitude 6.4, but actually they are going right laterally. Associated with the horizontal motion, some of them also exhibit subsidence. This is at an extensional quadrant of this earthquake sequence, so the downward motion makes sense, but it's really hard to explain these with frictional slip. The northern quadrant is also at an extensional quadrant. Here's a beautiful transition of fault behavior. The closest one is left lateral motion with some subsidence on the fault. The middle one almost no horizontal deformation, but with strong subsidence signal. The furthest one is right lateral with almost no vertical deformation. So how do we explain these observations? We then performed profile analysis for all fractures we could identify as prograding or retrograding. For example, for a fracture here, we get a 3 kilometer wide stacked profile and find the width and the amplitude of the deformation. Then we could compute the shear modulus contrast based on the 2002 Fialco science paper. If we perform this type of analysis and draw histograms of these observed or computed parameters, there seems to be statistical differences between the prograde and retrograde fractures. The colors here, light yellow, purple, and blue, are for all fractures, prograde fractures, and retrograde fractures. The amplitude distribution are largely similar, but the widths are wider for the retrograde fractures than the prograde fractures. The resulting shear modulus ratio for the retrograde fractures are larger, while most prograde fractures yield a ratio that's too small to be physically possible. The ratio is basically shear wave velocity reduction inside the fault damage zone. If we look at the formula, the deformation over width term basically produces these very low ratio when a much sharper step occurs at the surface, and thus the prograde fractures are likely to be frictional slip, and the retrograde ones are likely to be compliant fault deformation. So we developed a conceptual model to explain these observations. We assume all shallow faults are loaded into a critically stressed status from tectonic forces. Once the stress passes a certain threshold, it will develop into a frictional slip. However, this frictional slip does not fully release the accumulated stress, but rather turn the fault back to the critically stressed status. Naturally, with tectonic loading, the fault will have episodic frictional slip at the surface. In other words, interseismically, the shallow faults will constantly release stress. Under this scenario, when nearby earthquake impose stress perturbation on the critically stressed fault, the prograde stress will easily induce frictional slip. However, due to the existence of this buffer zone, the retrograde stress will lead the fault away from failure and thus exhibit as compliant fault deformation. The required stress perturbation for the fault to produce a backward frictional slip has to overcome that buffer and thus is unlikely to happen. This is why the retrograding fractures are compliant fault deformation, while the prograde ones are frictional slip. Here are some take-home messages and thoughts. So we find that the fractures near Ridgecrest have very different mechanism. Prograding ones are likely to be frictional slip, and retrograde ones are likely to be compliant fault deformation. And with the help from nearby earthquakes, satellite interferometry could help discover many new faults, especially at low strain areas. Compared to the faults near Landers and Hector Mine, these faults we found are essentially very young. The damage zone widths are a couple of hundred meters compared to 1 to 2 kilometers near Landers and Hector Mine. This is also good evidence that young faults also have well-developed damage zones. Also, these type of surface fractures may commonly exist in diffuse strike-slip fault systems like the East California shear zone. Based on our conceptual model, one of the most important implications is that much of the off-fault strain could be from inelastic deformation on many small faults. The interseismic strain release on these many small faults may hold account for the shallow slip deficit derived from the main rupture. Come to our poster 104 to talk to us if you are interested. Thank you.